My co-authors in this work are Associate Professor Sandra Mussolini and Professor Farid Abdul. The outline of my presentation is as following. Firstly, I will introduce the general motivations behind this work. Secondly, I will detail the constitutive equations presenting the mechanical modeling used in this work. Then I will present some relevant numerical results of our numerical tool, and I will finish my presentation by some concluding remarks. So the main objective of this work is to study the effect of plastic anisotropy on the ductility limit of metallic thin metallic sheets. This effect has been widely studied by using the Marciniak-Kozinski approach, for example. But the problem with this approach that is the ductility limit is strongly dependent on the initial imperfection ratio. In order to avoid this independency, we use in this work the bifurcation theory. So the bifurcation theory will be used instead of the Marciniak-Kozinski approach. So in order to obtain limit strains to obtain ductility limit at realistic limit strains, the bifurcation theory should be coupled with mechanical modeling that presents some softering behavior. In this work, the softering behavior is presented by the nucleation, growth, and coalescence of microgoids. So the GTN, or an approved version of the GTN model, will be used to model the mechanical behavior of the standard sheet. Compared to the initial version of the GTN model, the approved version takes into account the plastic anisotropy of the dense matrix. So with the use of with the coupling between the bifurcation theory and the approved GTN model, we are able to study by numerical approaches the effect of damage and the plastic anisotropy, or the combined effect of damage and plastic anisotropy on the ductility of metal sheets. So what about the constitutive equation of this approved GTN model? The first equation is the yield function. The first part of this yield function in black, it's exactly the same of a dense matrix without damage. The second part is the contribution of the damage, and we have here F, which is the scalar damage variable. The plastic anisotropy is introduced into parts. The first one, trough, the X equivalent stress which is dependent on the Langford equations. The second part is trough, this scalar equation K, which is also a function of the three Langford equations. To this yield function, we add the isotropic hardening of the matrix, which is defined by the Swift isotropic model, the flow rule defining the normality law, the relation between the plastic strain rate and the derivative of the yield function by the stress state. After that, we have the equation that describes the evolution of the damage evolution, the evolution of the scalar F, which is the sum of the nucleation part and the growth part, and we add to these two parts the void coalescence, which is introduced in the initial GTN model. So in order to predict the ductility limit, the previous GTN model is coupled with the Rice bifurcation criterion, or the bifurcation theory. This criterion assumes that the ductility limit is reached when the acoustic tensor becomes singular. The acoustic tensor n and n becomes singular. Otherwise, when the determinant of n and n becomes equal to 0. Where n is the normal to the decaying band, L is the analytical tangent modulus. This tangent modulus is expressed as a function of CUP. CUP is the elastoplastic tangent modulus, and other convective terms. The CUP in terms is expressed as the following form. So before using the coupled model between the bifurcation theory and the GTN model, we try to validate the implementation of the GTN model. In this case, we compare, we simulate a finite, the behavior of finite, a single finite element subjected to initial tension, and we compare our predictions with some reference results from the literature. And we have here the evolution of the initial tensor as a function of the initial tensor stress as a function of the initial tensor strain, the evolution of the damage variable also as a function of the initial tensor strain. We observe easily that our results are very close to the reference results which validate our numerical implementation. Now we try to apply this development model to study the ductility limit for three virtual materials. First one, the first one is an isotropic material defined by the three Langford equations which are equal to 1. The second one, the second and the third Langford equation are equal to 1. The first Langford coefficient is equal to 1.4. The third set is defined by a low Langford equation. Here I plot the evolution of the first component of the tangent modulus, which is defined here. The tangent modulus, the fourth of the tangent modulus. I plot the evolution of the first component of the tangent modulus with the case of a plane strain state, and I plot here the determinant, the evolution of the determinant of the acoustic tensor as a function of the initial tensor strain. And we can observe easily that the ductility, which is defined by the singularity of the tangent modulus, the singularity of the acoustic tensor increase with the Langford equation coefficient. Here, I try for the same materials to plot the whole range of strain paths defined from initial tensor state to equidiaxial tensor state for the three sets. And we can, this result confirm the previous result that the ductility increase with the coefficient, the Langford equation. And we try here to understand or to analyze the effect of the plastic anisotropy on the evolution of damage. So the conclusions of my work are as following. An approved version of the GTM model has been implemented in the finite element called Abacus as user materials with an implicit algorithm integration. The developed model has been coupled with the bifurcation theory, or the Rice bifurcation theory, to predict the ductility limit of thin metallic sheets. The predicted ductility limits in the form of four big limits diagram show strong sensitivity to the plastic anisotropy of the metallic sheet. Thank you for your attention.